Thank you very much for inviting me. And when the invitation came, I thought, what will be right subject to talk here? So you will judge. Okay. So let me start. Now, what I'll try to do, I will try to talk about some type of statistical inference related to optimization. Some of the results that I will talk today, and I will try to give general picture of that, going way back, maybe 70, 80 years. Some results are reasonably recent. There's a huge literature on what I will talk about from different points of view. I didn't give you references. Sometimes I'll probably say some key names, and so if after the talk will be some interest what I'm talking about and somebody wants to ask me a specific question about specific reference, specific paper, I'll be very glad to talk and give that. But again, when I wrote the slides, I didn't put any references so far. Okay, so let me start with some very basic problem. Suppose I have certain type of problems, and if we look here, okay, in very general form, and I will give examples, various examples. Suppose we want to minimize, solve certain problem. We are given as say expectation, okay, and but we really do not, for various reasons, we really do not solve this problem directly. We approximate it in some statistical manner. And as we'll see, as I'll discuss examples, there are two very different ways of looking at that from statistical point of view and from optimization point of view. Also, some theory about that will be somewhat similar, but a type of questions that one will ask about that can be very different. And then we have some data which we can collect, and this will be probably statistical approach given the data, or we can simulate, say, by Monte Carlo, and I'll talk about that more specifically. So really we cannot, for various reasons, we cannot really solve this problem, which in statistical language will be, say, true problem or population problem. We approximate it. Okay? So in a very general form, okay, given the data, given the observations, we replace the true distribution of this, say, random vector, or some even more, I will see even more general constructions, by its empirical one, based on observation. So we replace this true problem by some type of approximation. And our approximation is random, because it depends on random data that we replace, right? This is called empirical distribution. It's random. So the whole thing is random. And we solve, instead of this problem, we solve this problem. How we solve that, it's of course big question, and we had many talks about optimization. I will mainly not talk about that. It's very important, of course, but my talk will be by solving this problem, what we can say about optimal value and an optimal solution, viewing this as some type of estimates of what we really want to solve for the true problem. Some type of statistical inference of that. And again, the next, and I will give now several examples which will probably motivate what I will talk later. Okay. Now, the first is absolutely classical example. Going back to work of Fisher, I don't know, maybe 80 years back. I suppose everybody knows what is a maximum likelihood. There is some parametric model, okay? And we want to maximize that with probably some these constraints of the sum of the parameters. This is likelihood function, which is just the density of that. If I take the logarithm of that of the product, okay, I will have the sum. This is the reason. And then when we take the sum of that by the law of large numbers, it will converge to expected value of that. So from the point of view that I'm talking about, that one can view this as approximation of this problem that we really want to solve in some sense, or it's better to say it's converged to that. Okay. So then there's a classical results, and the classical results about consistency of that. This problem, if our model is correct, right, and under some regularity condition, identification, all that, has this true parameters as minimizers. This is the classical results. So there's a classical statistical inference of that. For example, convergence of that. So as the samples become larger and larger in some probabilistic sense, what we will get, they will converge through the true values. And there's also central limit theorem type of results of the asymptotics. Right? What we can say about this solution of that, which is main interest. No, classical is information, Fisher information matrix, and so on. So what I want to emphasize here when we talk about that, how we view that from statistical point of view, which will be quite different from what we'll see in a moment, how one can view that from completely different point of view of solving stochastic programming problem. Here we view these observations, and this is a standard notation in this area, as a data. We collect the data. Okay? We simply don't know what a real distribution is. We model it in a parametrics case. This number of parameters in a classical case is finite. And then we solve that, and we hope that reconstruct this true distribution, and so on and so on. Okay? Now, let me give you another example, and maybe a short story about that. Okay. Now, we had many talks in optimization. So this is what is written here is a classical, what today call semi-definite programming problem, right? In modern language. And this terminology is probably, I don't know, 25 years, something like that. Now, this type of problems in statistics, people solved much long before that. Of course, it was a different type of the terminology and the time that people, before development of interior point method and all that, the algorithms were not as powerful and all that. The classical example in statistics is a factor analysis. In fact, when long ago I started to do my PhD, and it was long ago, probably most of the young people here, which at that time were still not born at that time. Okay, I was given a problem, and at that time I didn't know much about statistics or optimization. It's probably overstatement. I knew nothing about optimization or statistics. So, and the problem was the classical factor analysis, okay, which is also going back to maybe more than 100 years ago, this modeling. And the classical, this time, this factor analysis, which was mainly used in psychometrics. Today, they use it in many different areas, okay. Given a covariance matrix, and we can change its diagonal elements, okay, how much I can reduce the rank by simply changing diagonal elements of symmetric matrix. And the problem that it's one of the way of looking at that. The problem that I was given was this. Of course, now, according to the model, this covariance matrix should be positive semi-definite. This matrix was supposed to be covariance matrix of the arrows, so it also should be positive semi-definite and diagonal. One assumes them to be uncorrelated or more generally independent. Here I didn't write these additional conditions that all diagonals here should be non-negative. And the question was just to minimize the trace of that subject to these constraints. And you can see that this is in modern language, and this was long before this modern development of semi-definite programming. This is one can view that as a semi-definite programming problem. And one of my papers was start to develop some type of numerical solutions. This when I start to learn about optimization, especially non-smooth, non-differentiable, because it's naturally happens here. It's one can formulate it as a certain optimization of eigenvalues which are not differentiable, and also statistical analysis. Because what we really have, right, when we look at this covariance matrix, which is a statistical language, one will say population covariance matrix, we estimate it from the data, given the data. And the fact is, and this was the first results, that by changing the diagonal elements of symmetrical matrix, one cannot reduce rank too much. Of course, if this is diagonal matrix, one can reduce it to 0. But if I'll take it at random, in some sense pick it at random, I cannot reduce rank too much. And there's some results. That was one of actually my first paper. And the other question was how it's related to this problem, which this is a convex problem. Even then, at that time, for small dimensions, it was possible to reasonably solve that. Okay? So in a modern language, one can look at that in far more general setting of semi-definite programming. This is it's one possible formulation of that. It's linear. And the question is, if we replace the population covariance matrix, which is unknown, by the sample matrix, which of course this introduced error, what we can say about the statistical properties of optimal value and optimal solution. To get statistical properties of optimal value is not that difficult. And this is basically, I'll talk about it later, is classical delta theorem, just linear approximation. It's much more sophisticated to get this statistical inference of the optimal solution of that. And that this is a relatively recent result, which all the development of this sensitivity analysis, that it's based off linearization and all. And it's interesting that it's very drastically different here from the case when one look at a linear programming. The curvature start to appear here, which produce a certain type of central limit theorem. Yeah, yes. Okay, thank you. Okay, I can see it here. Okay, so it's one example. But the setting here, from this point of view, is very similar. We have the data, right? We estimate, and what statistical inference one can say about that. So again, there's a publication. Somebody interested, I can talk about that. Now I can talk about this from optimization point of view, which is very different way of asking the question and different way of looking at that. Right? Suppose I want to solve this problem that I wrote it from the beginning. Okay? And this is our objective function. Supposedly I know that. And supposedly I can compute this reasonably efficiently for given x and given really this value of this. But still I really, even if I know that, how to compute the expected value? It's integral, multivariate integral. And when dimension of that is large, 10, right? This one, it's not something that can be done easily. And one of the possible way, and only in very rare cases, one can write some formulas to to compute that. So one of the popular methods to do that is to use in Monte Carlo, random. So what is the difference then? The difference that when I look at it here, that I generate sample by using Monte Carlo, and the type of the constraint that I have is computational. Right? Because at the end, after I approximate my original problem by this one, I still have to solve the optimization problem. I wrote it in a very abstract way, but one depending on dimension and all that. And if I have a mechanism that produces these random numbers, again, the constraints are very different. In statistics, there is data that you have. To collect more data is sometimes not even feasible. Here, it's a computational question. So you see, very different type of two questions that I ask. Also, the theory, theory that somewhat relates two of them. There's two approaches. In modern language, it became known as the sample average approximation method. Also, the idea of this type of Monte Carlo is going also way back. It's probably as old as Monte Carlo method. It's going back to development during Second World War with development of computers and all these names of von Neumann, Ulm, and people like that. Okay, so what was reasonably new with that is that it's known that a Monte Carlo method, when one approximates this integral, the corresponding integral, the expected value convergence is very slow. By central limit theorem, it's of order 1 over square root of n. Right? There's a lot of talk about quasi-Monte Carlo methods. Probably I will not talk about that. But nevertheless, in principle, one cannot generically compute a multidimensional integral very accurately. Okay? So all this development of this statistical inference of that, and I'll try to talk about that, led to some type of different view on stochastic programming. And this is a classical example of two-stage stochastic programming. Now, if you see it first time, it's probably I'll say probably something words after that. But basically, the objective in two-stage programming, the objective function is a result of second-stage optimization. And if it is linear and not too large, one can reasonably efficiently compute that for different value of x and that, and then one can write optimization. I will talk about that later. But at this point, I want to emphasize this type of questions that we ask here is very different. One of the questions that is natural to ask, how large the sample size I will need to ensure certain time accuracy of the solution here. And it's random. So I will need to talk about that again, some type of statistical inference about that, statistical analysis of that. It comes naturally here. Also, the purpose of that is very different from what I looked before. Okay? Now, this is what I showed you was just two-stage, which in some sense is a static problem. Here, when I look at that, this vector of uncertain parameters, which are modeled by random distribution, there's a big question how to model that. Do we know anything about that? One can go on and on and on. I'll have no time to talk about that. But at least it's finite dimensional. Okay? There are also, when you look at this decision variables, also finite dimensional. They're very natural questions where we immediately come to functional spaces, infinite dimensional questions. Okay? So, and this is a multi-stage problem, and we make decision at stages. There's a dynamics here. And this type of problems were considered in applications from different point of view, maybe by 3 different communities, as far as I know. There were people in stochastic programming, again, going back to development of linear programming and optimal control and Markov decision processes. In stochastic programming community, it was always motivated, and the solution is just brute force. How to solve that? Okay, and until maybe 15 years ago, or maybe a little more, it was all dominated, this type of questions were all dominated by generated scenarios. In other words, if you look at that, what does it mean that one solved that? This one make observation, then one make decision. One make observation, one make decision. So in principle, this formulation that is given here, the solution is some type infinite dimensional, because one has to give to the user certain type of function of the data as the process is going on, what to do, observed what happened in the past. So the solution of that is not just finite dimensional vector, it's functional. And there's many problems here. It's really just modeling problems, but from computational point of view, how one can put it in a computer even. Computer is a finite machine. One has to make some type of discretization. And in stochastic programming, it was dominated by generated scenarios. In statistical language of probability, it's a sample path, what can happen in the future. So how to analyze that? What does it mean? Even the question, what does it mean to solve such problem, was not clearly defined. Because if I generate possible scenarios, and if you look at the book of that, it's usually some type of tree. But what will happen in the future with probability 1 will be different from the scenarios that one signed to that. So what to do in this case? Okay. So in the last 15 years, I think there was a very big progress in our understanding of limitations, what we can do, and also developing some numerical algorithms and all that. I will not have time to talk about all of that, so let me concentrate on something. Okay? This is what I said just now. The optimization here is done, at least the way it's formulated. One gives to the user policy. And it should be feasible. It should satisfy feasibility constraints with probability 1. Okay. Now, the immediate point here is that if I will try to approximate this type of thing by scenario 3, the number of scenarios explodes very quickly. If I want to do it in any reasonable way, and we'll see some type of estimates of that. So I still think we have no clear way how to do that. Probably it's in principle impossible to solve such problem in some reasonable way. It doesn't mean that we have not to do that, because the class of this problem is too important, but at least to understand what we can do and what we cannot do. And this is a big question. Now, in other applications of all of that, and this is also started about 15 ago, this was a famous paper. The concept of the risk and the analysis of that going way centuries back. Okay? But it was a famous paper was published by 4 authors, and it came from financial applications, where they say, okay, So far what I showed you, this one optimized that, try to minimize that when you have some randomness or uncertainty, one model that is a random distribution. Why is a good question. And then one to optimize this on average. What really will happen is will be maybe very different what you see on average. Why one optimize on average? The justification of that is law of large numbers. So if I will, under certain condition, I'll do long enough, I'll get it on average, this I'll get. But it doesn't say anything about the risk of that. And people don't like when the risk, they don't, this one of the application that we talk with this development is control of the planning of this power generation using the water. One doesn't like that 1 month the price of the electricity will be 100 times more than on average. And they tell to the users, don't worry about that, over 10 years it will average out. People sometimes don't like that. And this is type of, these ideas came from finance. And these people formulated 4 axioms or conditions which came very naturally and turned out to be very productive from intuitive point of view and from mathematical point of view. So from this, if I want to formulate such problem under uncertainty, I have to assign some numerical value to that, which I minimize in some sense, try to minimize some sense. And one of the possible take expected value, it's a linear function. Here, it's instead of linear function, it's replaced by convexity and some other very natural conditions. This is monotonicity, so we have minimized their cost. It's also possible to formulate and maximizing the profit. But if I minimize, if I have 2 possible realizations and one is always better than the other, it's very natural, right, that I will have to prefer this one. Well, okay. And there's it turns out that this is in many ways a very natural condition. For example, this one, if I invest $1 or try to invest $1,000, it's proportional. One can do more general like that, but it's good enough. Now, and here we have the concept of law invariance. It also has different names. What law invariance means, that it's also all story in probability, how we model random variables. Before Kolmogorov, I think, at least, it was by looking at the distribution. Then came Kolmogorov and say, okay, we can model with this probability, and then it's just, from this point of view, random variable is just measurable function. I can add that, and I can multiply it, become a linear space, and so on. But what I observe, it's my construction, what I observe, of course, or I can model in some reasonable way, is some type of distribution. So in that, from this point of view, that if in many applications, there is a reference type of distribution, not always, but sometimes, and then there's a natural concept of law invariance that's saying that really the numerical value that I assign to different possible realization of the random variable should only depend on the distribution of that and not on a particular realization of that. So this is called law invariance. And one of the most important examples of such risks, this is it has many names, was discovered and rediscovered by many authors, okay? And in modern, at least in the financial literature, it's called average value at risk. It's also, you probably know, it's also called conditional value at risk, many other names. And it has different forms. In that form, one simply takes the certain type of integral of quantiles, right, upper quantiles of that. In that form, in economics, I think it was used 100 years ago, some maybe like that. The top quantiles, and then one integrate that. This variational representation of that, I think, due to Rockefeller and Uriasyev, which is very convenient for many applications. And for many reasons, this is this one is the most important example of this type of risk measure. It satisfies all these axioms, and it's also law invariant. And I'll show one of the reasons why it's so important. It can be a basic block of doing this construct in its very general way. So if I look at that way, right, it's very natural, given the data, I can look the corresponding distribution function, empirical distribution function coming from the data, and I can approximate this, which involves the integral, by the corresponding sum. This is equivalent to what I showed you before. Okay. Now, one of the reasons why this is so basic and so important, and it's certain theorem, not completely trivial. It shows, and this is the name of this Japanese statistician, or actually probabilist that first showed that, is that any risk measure that in this terminology they call it coherent risk measure can be represented in that form. One can take convex combination with respect to that. This is some type of probability measure, and they take some maximum of that. Anything can be represented like that, and one can write it explicitly for different this type of coherent risk measures. So if I will use this type of the variational representation of that, it's possible to show then coming from that I can write it as min-max. Very abstract form, and actually infinite dimensional, because this function here will be functional. Right? So in general, if I have some such risk measures, right, because they're law invariant, they only depend on a distribution. So if I have the data, which I can look at that from 2 points of view, I can look at the collected data, or I can look at the simulation which allow me to solve such type of problems, I can replace it by empirical one. And the question again, what will be type of distributions that? What will be statistical inference? And there's some big progress in that. Okay, I'll show you. Now, maybe I'll say just even now, surprisingly, and this turns out that it was very difficult, there's some very technical problems to prove the corresponding asymptotics of that, which is more or less clear what it should be. In some cases, it's even possible to prove that. I'll show you some general technique that one can do, but we still don't have complete analysis of that. Also, there's some recent results on that. Now, when we look at this from statistical point of view of that, there's several classical questions. One question is, if my sample size become larger and larger, will I have convergence of that? Okay. This, in statistical language, they call it consistency. The classical paper on this for maximum likelihood, going back to Wald, I think it's 45, 49, something like that. It's classical paper on this, which first prove consistency of rigorously under some conditions, of course, consistency of maximum likelihood estimated. Okay, so, and there are some very general results about that, and it turns out to prove such consistency, the convergence, not trivial, but not too difficult. Okay, now we have very strong results about that. I'll show some. Okay. One of the bases of that, it's possible to show this Glivenko-Contelli type of this uniform convergence, uniform loss of large numbers. Again, some of these results are classical, going back many years back. Okay, this is one of the possible theorems of this is relatively simple theorem. Of course, we have the classical law of large numbers by Kolmogorov law of large numbers for fixed x. The difference is that I want some type uniform of that. It's not that difficult. No, this is one of the possible formulations of that. if I will have this type of convergence on compact sets, from that usually follows the convergence of the corresponding optimization problem. And this is not that difficult. A little bit better in some sense, especially when one has the constraints. And here probably I should say that in classical statistical, constraints didn't play, at least the classical statistical theory constraints didn't play that much of the role. Of course, there are usually some simple constraints. Today, probably it's changing. But from optimization point of view, this is very important. Okay? So when one deals with the constraints, it's sometimes more convenient to use this is called what is called epiconvergence. And this epiconvergence is some type of convergence in terms of epigraphs. Again, I don't have much time, so this is not that important at the moment. And this is one of the results for these risk measures. It's possible to prove its consistency with optimization, which is not completely trivial, by the way. Okay. Now, again, I have to move on. The next thing after one proves some type of convergence, if it doesn't converge, not much to talk about. But it's far not enough if one wants to justify certain type of method from both points of view, from statistical and from optimization. So what are rate at which it converge? It's one question. And can one estimate the error somehow, the error of my solving the true problem by its approximation? So in, again, classical statistical analysis, one does it by asymptotics. There's a classical result about Fisher information matrix. There are many questions how good this asymptotic is, but in when I teach the classes, it's all this in softwares, in packages, when they compute a variance, confidence interval, testing hypothesis, and so on, and so on, and so on. So this central type of this. And this is already much more sophisticated, much more, in general, much more difficult than to proving just the convergence. And so if I will, and some of the results are really quite, I will say, I don't know, classical results are somewhat pessimistic. If I'll fix the value of the x, what is written is just the average. And there's under certain condition, classical central limit theorem telling me that if n become larger and larger, it will converge to normal distribution with certain variance. So it will all tell me that even if I don't do optimization, but I just look at fixed value, I just want to estimate that. The rate at which it converge is 1, in statistical term, 1 over square root of n. Okay? Now, then there's also classical technique in statistics, which is called delta method, which basically linearization. In finite dimensionals, it's very simple. Right? This is what is written here. So if I will start something which from the beginning I know that it has convergent distribution to normal distribution, simply applying classical central limit theorem by averaging, I make some transformation of that, maybe non-linear but smooth. I just approximate it by linear, and then for linear transformation, when I have this linear transformation, multiply a random vector which has normal distribution by matrix, I know that will be again normal. This is a basic property of normal distribution, and this is what is called classical delta theorem. And it works well for infinite dimensional setting. Now, for quite a number of years in the last century, people tried to extend that to infinite dimensional setting because it appears some sense naturally. And this is one of the formulation that it turns out to be very, very useful. And it's look quite abstract. Okay. We're talking about Banach space, but you can think about it, and I'll immediately will give you very simple implication of that. Okay? You can think about some functional type of spaces. And we have the mapping from one to another. Typically, this one is just real line. We look at, or finite dimensional. We look at the mapping of that. And then we approximate it by looking at the directional derivative of that. If the directional derivative is linear, it will be usual linear approximation. No, there's a Gateau derivative, there's Frechet, and some others. This is very often is called Hadamard derivative. That it is we want something stronger than just directional derivative. All direction, it should be okay going along the curves. That. In many cases, it's possible to compute, right? And then there's this type of result. This is turned out to be very useful infinite dimensional delta theorem. And I'll immediately will give you application. Proof of that is not completely trivial, based on some quite sophisticated things about that. But the idea is very simple. Right? We look at that, and this is at some point. This is usually the mean of that. Okay? It doesn't need to be linear. If it is linear, we'll typically have some normal distribution, but the directional derivative by itself always positively homogeneous. Okay? So then if we have it something like that, right, then it's simply just some type of linearization. We will have this result. This means it's a standard notation in statistics. That means it conversion probability to 0. From that one, you can immediately will get convergence and distribution by Slutsky theorem. Okay. Now, this is a first order approximation. From one can go one step further and look at the second order approximation. Okay. Which in some cases give additional information. And there's a natural generalization of second order directional derivative, which is written here. It's like, no, one has first order derivative, one can have look in principle at the second order derivative. And there's a generalization of this delta infinite dimensional also to second order. If you look here, this is a value that we look at that, and then we take out the linear term, and then we still have convergent distribution to the second. And I'll give you examples of that. Okay. Now, in principle, I suppose one can go to higher order derivatives, but the point is that we can, at least I don't know how to compute the higher order derivatives in non-trivial cases. Second order derivatives, there's very well-developed theory for optimization how to compute it. And I'll show you formulas. Okay. Now, and here we immediately have some result which looks very simple. The final result is looks very simple. And the proof of that is very sophisticated. And in fact, I don't know how to prove it in elementary way. And the idea is the following. Okay, this is very simple condition. These two very simple conditions that we have. Yeah? We need it's a finite second order moment at one point, and we need certain type of Lipschitz condition on the objective function. Right? Then what is the idea of that? We look at this function in some functional space. Okay, and when I minimize that, I can look at that as some mapping of functional from this function to the real line, assuming it's real. Now, a real number. Okay? The next point, and to compute the corresponding derivative is not difficult. It's known, and it's given by this. So this is a difference between them, and this is a set of optimal solutions for the limiting value for the mean. So of course, if it is unique, right, we'll have some type of linear. This directional derivative will be linear. In general, it will be non-linear. If we have the set of optimal solution of the true problem has more than one optimal solution, and it has a lot of effect on the statistical in application on the statistical analysis of that. Right? So Then we have this. This immediately leads to this type of result, which is quite old result. Okay, for this SA method, one can look at the SA method, or one can look at generally this for statistical application, and basically say that if this is a true the optimal value for the true problem, this is approximation that we get by approximation it by random. And I have central limit theorem type of result of that, okay, which is telling me that the convergent distribution to minimum of a certain Gaussian process. And it's again, as I said, based on two very non-trivial things. This delta theorem, infinite dimension, is not trivial, and this is this corresponding this what I can look at this. Right, as a certain type Gaussian process, this conversion to distribution Gaussian process is not trivial question. But the final result is very simple, and amazingly simple. So in particular, if this the set of optimal solution of the true problem is just one point, singleton, I will have this asymptotic normality. It will converge asymptotically to normal. If it is not one, it will be the minimum of that, depending on how large this set is. And indeed, it was observed also empirically on that. It will be very, when we try to look at this statistical inference properties of that, it's very important how large the optimal set for the true problem. Now, what is maybe even more interesting, one can get second order asymptotics of that based on second order delta theorem. The formulas which involved are quite clear. The difficulty that, and there's technical difficulties to get the corresponding central limit type of functional theorem in appropriate space. And there's no, at least I don't know the clear solution for that. But the formula itself are known, and it's also very much related to modern perturbation analysis, also which relatively recent, all right, and not trivial. In particular, then if we again apply that to this using second order delta theorem, we immediately will have this type of expansion of the optimal value. This is we fix the point. One needs considerably stronger condition here in order to get that. The optimal, this true problem should have unique optimal solution, and then we have this second order term. So if I take the difference of that, will converge in distribution of that. Also, if I want asymptotics distribution of the solutions, I need to go to the second order analysis. First order analysis doesn't give it. And it's become very non-trivial thing. In particular, one can look at these give formulas for the bias of this type of things. Right? When it's quite clear that when I do minimization, if I do the point and I average that, it's unbiased estimator, but I minimize that, they push it down. So if I have several random variables, which is unbiased estimate, if I take the minimal of that, it will be biased. The more of them I take, typically it will be more, the more bias I will have. And so it allows in certain case to estimate the bias of my estimation, to give the formula by looking at the second order term. And in this case, the bias is of order 1 over n. And it was why it's of order 1 over n, because here we assume that this true problem has unique optimal solution. Typically, if the true problem has more than one optimal solution, the bias is of order 1 over square root of n, which is the same order as standard deviation of that. And this was also observed in practice. And this is one of the problems with this SA method applied to solving the problems. Now, in particular, one can look at this example of this of the average value at risk and immediately will get asymptotics of that. even more, right? And this is a with reasonably simple formula. This is first order asymptotics of that, no, depending on what is the variant. And one even can get second order asymptotics of that using second order. As I said, it turned out to be technically, with some very difficult technical to generalize that to general this coherent risk measures. Also, some results are available about that. If somebody interested in their papers on that. Okay. Now, maybe I mentioned this also min-max type of theorems that in many applications, and one can formulate it as min-max type of problem. This one of the applications that I show that with coherent risk measures. Very often it's very natural. So this delta theorem can be also generalized to that, and one will get min-max type of this sample average approximation, and one under similar conditions one also get this first order approximation of that. So when I have this min-max type of problem, there's a certain type of convexity, convex concave. There's a saddle point of that. So if they are singletons, I'll have a asymptotic normality for the value. Now, I just have just few minutes. Let me talk about something very different. So, okay. So far, I talked about this asymptotics, and this is a quite well-developed theory. Another question that is very natural to ask in this type of applications from the point of view of optimization. Right? How large I need the sample size, how many points I need to generate by Monte Carlo method in order to solve my true problem, which I simply cannot solve because I cannot compute the expected value of, let's say, or this multivariate integral with reasonable accuracy. It's some type of discretization. By generating this finite sample of that, eventually I'll get just optimization problem, which in some case can be solved, say linear. Okay. Now there's a classical again theory about that applied in probability, this large deviation type of bounds. Okay. This is where, and basically you get this. It's different from this central limit theorem type of results. These are exponential. Okay. Typically for maybe I'll say something about that in a moment. And this is very much related to a sample, what we'll today probably will say sample complexity of solving these stochastic programs by this type of randomization, by these Monte Carlo methods. Okay? Because the value, how large the sample size should be in order to reasonably solve that with reasonable accuracy, tell me how much effort I can put in the computations and what I can expect from that. Okay. So one of this, and the first results of that is going back to maybe 15, 17 years ago, that for static problems, when one doesn't have dynamics, one can often, under certain conditions, solve that with reasonable accuracy in reasonable computational time. And this type of estimates of that one can get. Of course, when one try to solve the stochastic programming problems, this type of, one in principle cannot hope to solve that with accuracy of, I don't know, which is common in a deterministic case, say with accuracy of 10 to the minus 6 or 10 to the minus 5. Right? And if one can solve this type of problem with, say, error of 1 or 2%, it's practical application. It's usually more than enough. Moreover, the errors that come in from modeling part of that usually far bigger than this type of accuracy of that. Trying to solve that with accuracy 10 to the minus 6 can be simply misleading. And this type of analysis, and it was tested on many, many practical applications. Of course, there's always limit to this, and it's not every. But it turns out that the static, say, two-stage problem in many cases can be solved with reasonable accuracy, with reasonable computational effort. And there was methodology developed there, and became quite standard in many, many applications. Okay? And this is one of the first results of that. Here, right, this feasible set is finite, but probably it's a combinatorial of huge size, but it's under logarithm. So, and there's some constants here. And one of this, when look from the point of view of optimization from error, the error is of dying. Okay, okay. Anyway, this battery probably die. No, it works. Epsilon of epsilon square. And from Monte Carlo point of view, this one cannot do much more than that. And really, one cannot from this point of view, one cannot really improve this rate. More generally, for, say, continuous this type of estimates of the sample size, this is theoretical estimates. It's not useful from practical purpose because it's far too conservative for practical calculations. But it never gives us ideas that what one can expect of this type of methods. Just, yeah, okay, I'll finish it in a few minutes. All right, so for example, this is error that we can expect. And this is the small n is this size of the decisions, this how many decisions that it appears here. And this is we can give guarantees only with certain probability, which is okay in applications. Okay, no, this is some. Maybe just last few words about multistage case. And it worked very well now. It became standard, what I'm saying. When one go from static case to multistage, situation is completely different. And before that, when it was from point of view of term of scenarios, it was not really big difference between two-stage and multistage. No one has 100,000 scenarios, one do decomposition, put in parallel, and so on. Here it's completely, the point of view is completely different. The sample complexity is completely different. And just the question, how we generate these scenarios is a very important question. I have to make certain assumptions how the process is going on. The simplest is that I have independence from one stage to another. In that case, if I want to sample, to discretize that, I only need to look at the marginal distributions. If I have complete dependence, how do I even put it in a computer? And then I don't have much time, but it's possible to show that from this point of view, the sample complexity explodes. It starts to grow exponentially. So if by using Monte Carlo for static case we're able to solve that to some extent, it dies here. Because also here, the number of scenarios one needs to grow exponentially with the dimension of state variables, but also with number of stages. So been some progress, and I have to finish now. It will be another talk to talk about all this progress that one made, but there are probably some limitations one can do here. Okay?